Okay, in our last chapter, we're going to go ahead and we're going to look back at scatter plots and linear regression. And we're going to go ahead and talk about several different things with scatter plots, but we're going to end up doing some tests with them that we've learned in the second semester. So we're going to go ahead and review a little bit of chapter 3. So as you can tell, we're going to do some chapter 3 review. Scatter plots allow us to visualize the relationship between an explanatory variable, and our explanatory variable will match with our x-axis, and then our response variable, which will be graphed on our y-axis. Now, usually when we do scatter plots, we end up calculating a correlation, which is our R value, and it allows us to describe how closely our data fits to a linear pattern. So how linear is it? Now, our correlation values are always between -1 and 1. A -1 means the data forms a straight line. It's a perfect straight line, but it has a negative slope. So as one value increases, the other one decreases, is the relationship that's occurring. And then if R equals 0, the data is truly a random pattern and does not come close to forming a line, so there's going to be no relationship between them. And if R equals 1, then the data forms a straight line with a positive slope. So as one value increases, the other value also increases in a perfect straight line pattern. Now, we rarely get the perfect straight line, but we will get stuff that's really, really close. Linear squares regression line. So this is our kind of prediction line, the line of best fit, some people call it. And it takes the data and summarizes the relationship between the explanatory and response variable. It is usually used to predict the value of a response variable. Now we have 3 different forms for a regression line. We have y equals a plus bx, and then we have y equals alpha plus beta x, which is just kind of a Greek version of the first one. And then we have our formula sheet version, which is y equals bo plus b1x. Again, with each one of these, our first value, a, alpha, and b0 are all going to be our y-intercept, and then we have our b, beta, and b1, which are all going to be our slope. And so our slope is always paired up with our x, kind of like when we, on Algebra 1 graph lines, where we have y, oops, I meant to make that a pen, y equals mx plus b. So the m, our slope is always with our x. But for graphing purposes, we flip this around in stats where b comes first plus mx. So we graph this first, and then we use the slope to graph the rest of our line. So how do we interpret our y-intercept? So this is going to be a key one that you're going to see. Interpretation of our y-intercept is it's the response value when our explanatory value is 0. So if I'm looking at age predicting height, then it would be my height. So what is the height when our age is 0? And so that's how we use it to explain what's happening. How we interpret slope. So slope is our change for every one x value. So the amount our response value changes for each increase of 1 in the explanatory variable value. So we're always looking at slope as a number over 1. And when we think of slope, it's our y value over x. So how our number on top, y, changes for every increase of 1 in x. Okay, other words. Residual, the difference in the actual response value and the predicted response value for a certain explanatory variable. So if we were graphing down here, and here's our scatter plot, and then we have a line of best fit like this, our residual is the difference between this actual value here and what we predicted right here. So if I do actual minus my predicted, because this is lower, I would end up with a negative residual. And that makes sense because it's below the line, so it would be kind of a negative value. And then here, the difference between my actual and predicted, so actual minus predicted, this is the residual, so this would be a positive residual. The purpose of a regression line is to make the square of those residuals added up as small as possible. Why? Because when you add up all the residuals, you end up with 0, because that's how we get that line of best fit. So instead of looking at making our residuals, when I add them all up, equal to 0, we're really looking at making the squares, because we're going to have some positives and some negatives. And so we're trying to make those values as small as possible. And then we have something called residual plots. So residual plots tell us if a linear model for the prediction equation is appropriate. And what it does is it takes our x values and then it plots our residual on the y-axis. And so what we do is we look for some sort of a pattern. So if we end up with a pattern like this on our residual plot, that would tell us that our original graph wasn't a real linear graph. And if it ends up being just very random, that's good, because that means our original pattern was linear and we can use a linear regression to plot that. So then our next key term is S, which is the standard deviation of the residuals. It allows us to examine the average prediction error. So if I start predicting off this red line of best fit, how far off will my answers be? And if they end up being too far off, more often than not, then it's not going to be a very good prediction tool for us. And then we have our R squared, which is correlation squared, and it's also known as the coefficient of determination. It is the proportion of the response value that can be attributed to the explanatory value alone. So it lets us know how much is that explanatory value really playing into what we're seeing with that response value, or is there a lot of other things in play there, other variables that may be affecting that and keeping that scatter plot with a low correlation, really, because it ends up more scattered. The more tightly fit, the more of a relation, the stronger the relationship is there to it. And so we interpret that by the regression line accounts for blank percent of the variation in the response value. So now we're going to go ahead and look at a sample problem. Many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause, now we have to be careful about that word, cause higher achievement, or do better students simply choose to sit in the front? To investigate, an AP Stats teacher randomly assigned students to seat locations in his classroom for a particular chapter and recorded the test score for each student at the end of the chapter. The explanatory variable in this experiment is which row the students were assigned. So row 1 would be the closest to the front and row 7 is the farthest away. Here are the results, including the scatter plot and the least squares regression line. So up here we have our scatter plot. We've got our regression line. Looks like there's a lot of scatter to that. And then here's our equation for the regression line. So here is our y-intercept. And here is our slope. And it says interpret the slope of the least squares regression line in this context. And so the slope is looking at how our y value changes, or our response variable changes. So how our score changes. So test scores. And then because my slope is a negative 1.12, that means my test scores are going down. So test scores drop 1.12 points for every row back. A student sits. And the next part that we want is not really the slope, because I had a typo there, but this should actually be the y-intercept. And so our y-intercept is 86. And so our y-intercept is saying, okay, when this is 0, so when my rho is 0, what will that test score be? So this is test score of 86 when the rho is 0. Now, does this totally make sense? Not really. And a lot of times, your y-intercept may not truly make sense in the context of the problem, because there is no rho 0. But it allows you to think that really, when you're thinking about this and making sense of our prediction line, our scores aren't going to get any higher than 86 based on the prediction line. Now, when we look at the data, of course, scores are higher than 86, but when we make sense of it by using this prediction line, we're not looking really of predicting the scores being higher than 86. Okay, so in this section, so that's kind of a review of stuff we've done before. I like reviewing the interpretations because I know that's where people struggle the most. So I really wanted to make sure we had that because we will continue to see that in this chapter. So now what we're going to do is we're going to start analyzing what happens to the slope of our line. And so we're going to start using our tests for that. So we're going to start with the population that we know the data for. We're going to sample many, many times and record the slopes of the regression line for each sample. And then we're going to analyze the sampling distribution. And this isn't really what we're doing. This is what statisticians have done in the past. And this is how we come up with the procedures that we use. So what do we find when this happens? Well, we find that the shape of our sampling distribution is pretty close to normal. The mean of the sampling distribution will be close to the true mean of the population. And the standard deviation of the distribution is close to the actual standard deviation of the population. And we've got this standard deviation formula, which is just a little bit different, because now we have the square root of n minus 1. Now from this, we can perform inference tests, which is our confidence intervals, and our significance tests, which we should be very familiar with. We've been doing them for months now. And we can do that for the slope of the regression line. And so the nice thing about a confidence interval is we can figure out what is the true slope. And if we end up with 0 being inside of our confidence interval, that means that there's a possibility that there's no real relationship between these variables. But if we end up with them both being positive, then we know that both values in the confidence interval being positive, which means the slope is definitely a positive slope. That means that there's definitely a positive relationship between these. So as one variable increases, so will the other variable increase, and so on and so forth. Now, to be able to do any of these tests, we have certain inferences, and now our conditions for these inference tests. And so now we're going to go from 3 conditions to 5. So we do have our normal random sampling, so well-designed random sample, randomized experiment. We do have a normal condition, but our normal condition is for the residuals. So we're going to have to calculate a regression line to be able to access those residuals. And then from there, we can graph those using a stem plot if we do it by hand, a histogram on the calculator, or my favorite, the normal probability plot on the calculator. And then we can check for clear skewness or any major departures from normality. So again, with the histogram, it tends to be a lot more work, but to really see if it's normal, and there's a lot more subjectivity, but the normal probability plot is pretty easy to work with. And then we have the independence. So still looking at random sampling, random assignment indicates independent observations, and sampling without replacement requires the 10% rule. And then we have our new ones, which is equal variance and linear. So for linear, we need to actually graph the scatter plot and make sure that the two variables are linear. So we graph the actual scatter plot. We look, hey, is it linear? And then sometimes it may look linear when it really isn't. So then we look at the residual plot. So we'll talk about how to look at the residual plot again. And then what we do is we also look at equivariance. So we're going to analyze the residual plot, and we're going to look at the amount of scatter. And we want to make sure that it's roughly the same for each possible value of x. And this really kind of comes into play here too with checking for normality. What we really don't want to happen when we're looking at those residual plots is to have a residual plot that looks like this. So here's my residual plot. We don't want it to be kind of residuals right here like this, and then all of a sudden it starts spreading out. And so we get a lot of scatter over here and no scatter over there. We want our scatter to be roughly even throughout. It's easier to see when we have more data points if we meet this equivariance. And when we only have a couple data points, it's really hard to see. And so that's what we're going to be looking for. So our problem, similar to what we're going to see, is we have this scatter plot. Again, the same problem. The seat row, so which row did the person sit in, their test score, and we have our line and our scatter. So we're looking to see, is it pretty linear? And so, yeah, scatter plot has a weak, because that's not a very strong, that's quite a lot of scatter. A weak linear, but it looks pretty linear. I'm not seeing any curvature to it. Linear pattern. But that's not the only way we check for linear. Because even though it doesn't look curved, now we have to go to our residual plot. And we're looking for some curvature here at our residual plot. And I'm not seeing anything. It looks pretty good scatter. So then residual plot has no pattern. Oops, pattern, forgot the A. So it is linear. Okay, and then random. So if we look back at our original problem, where are we? Where's the original problem? Many people believe students to investigate stats teacher randomly assigned. So we have some random assignment here, which is good. That means it's an experiment because we're looking for cause and effect. So we would say random assignment of seat placement. Okay, and then normal. So again, here I would really like to do a normal probability plot, but I didn't have all the data points available. So instead, I went ahead and went with their histogram. So we're looking to see, does this look pretty normal? It's pretty symmetrical, and it looks like we've got some pretty good boundaries. It may be a little heavy right in here and less heavy here, but overall, it's approximately normal. So our histogram of the residuals show no strong skewness or outliers. And that's really what we're looking for. Strong skewness or outliers, and we see none of that. Okay, so now we're going to go to our equivariance. So we're going back to our scatter plot, and we're looking at all these little dots. And we're looking to see, hey, are they really tight on one side and really spread out on the other, or are they all pretty well spread out? So we're looking at all these blue dots here that I'm making blue right now. They all look pretty well scattered. So even number of dots. Above and below. and there is even scatter on both sides. And so we look side to side because remember, we're trying to see if there's something like this, kind of like a ballooning effect where it gets wider and wider on right to left. So we're looking for even scatter right to left and then even amount of dots above and below. And so that's our idea with the equal variance. And then independent, because this was an experiment with random assignment assures independence. And that's what we're just going to be working on, just kind of checking out these conditions, reminding ourselves of the stuff that we just covered in Chapter 3. So you may want to have your Chapter 3 notes available, so if you need to get more in depth about how do I graph these sort of things, they're all there in that Chapter 3 note.